All right, in this first example, we are going to work on identifying geometric sequences. So part A, is the sequence shown in the table a geometric sequence? If so, write a recursive definition for the sequence. So let's write in what a geometric sequence is. That is defined as a sequence with a common ratio between consecutive terms. And that common ratio, we just use an R to represent our common ratio. So the question is, does this represent a geometric sequence? So the first column just gives us the term number. So here's the first term, second term, third term, fourth term, fifth term. And the column on the right tells us what that term is. So the first term is a 4, the second term is a 12, the third term is 36, and so on. So for this to be a geometric sequence, we should be able to take each term, multiply it by a common ratio to get to the next term. So can we take 4 and multiply it by something to get to 12? And we would say, oh, well, yeah, 4 times 3 gets us to 12. Well, does that work to get to the next term? Is 12 times 3 equal to 36? It is. Is 36 times 3 equal to 108? It is. Is 108 times 3 equal to 324? It is. So because we found that there is a common ratio of 3, this is a geometric sequence. So yes, it is. And they want us to write a recursive definition. You only need 2 pieces of information to write the recursive definition. You need the common ratio, which we figured out was a 3, and you need the first term. So up here we can see that the first term is a 4. So the recursive definition is going to be A sub n. The recursive is the one that has 2 lines. First you have to identify the first term for n equal to 1. So that's how a recursive definition will define the first term. So n equals 1 is the first term, which is 4. And then the rule is you take your common ratio 3 times the previous term, a sub n minus 1. That kind of looks like a 7. So there we go. And you're going to follow this part of our rule for every term after 1. So n is greater than 1. And there's our recursive definition. Okay, part B. Is this sequence a geometric sequence? If so, write the recursive definition for the sequence. So this one's not as obvious as the last one. Our first term is 12. Our second term is 9.6. Then it's 7.68. Then it's a 6.144. So that's not something I'm doing in my head. I don't know 12 times what gets me to 9. 9 times what gets me to 6.7. So you can check to see if it is a geometric sequence. So what the check looks like, is this geometric? That's all I mean by check, is you take the second term and you divide it by the previous term, the term before. So our second term, and this gets a little tricky to see. I think I said it wrong a second ago. You gotta look for the commas. So 9.6, 7.68, those are the terms right there. So the second term is 9.6. We're going to divide that by 12 and see what we get. And then we're going to check the third term, 7.68, and divide it by the term before that, which is 9.6. See what we get there. And then we're going to take the next term, 6.144, divide it by the term before, which is a 7.68. So if we grab our calculators and we divide these out, for the first one, we get a 0.8. For the second one, we get another 0.8. And for the third one, we get another 0.8. Because this is a consistent number, that is the common ratio. So our common ratio is 0.8. So again, this is how, if you take a term, divide it by the term before, And you do want to check all of them. Anything that you're provided with, make sure it's consistent through the whole thing. That's how you can find your common ratio. The other information we need to write the definition is the first term, and we can see that the first term is 12. So our recursive definition, a sub n equals, first line has the first term of 12 when n equals 1. And then the second line is the rule. How do you get to the next term? Well, you take your common ratio, 0.8, and you multiply it by the previous term. And you're going to do this for every term after the first term. So there's our recursive definition for this geometric sequence.